Greetings, Earthlings. Later today I have to go have some dental work done, which probably means I won't be able to speak very well for the next few days. But I wanted to get this video done, so I'm going to try recording the spoken part now, and then as I'm recovering, I'll do the video part and overlay my narration over it. See how that works out. So what is the video about? Well, I've written a microcode assembler. I wrote it in PERL. And now you may say, well, that's stupid. But actually, it makes a lot of sense from a standpoint of portability. PERL will run on Windows or Linux or whatever you might have. But it's slow. Well, as it turns out, it's fast enough. I'm not worried about ultimate efficiency for this purpose. This is not production code, it's used to generate the microcode, and then it'll be basically throwaway. So if it takes a while to run to assemble the files, that's no big deal. As it turns out, it's actually less than 100 milliseconds to do the actual assembly, so no big deal. If it was 10 seconds, I could live with that, One of the nice things about doing it in PERL is I don't have to write a symbol table package, because that's built into PERL, basically. And I haven't actually programmed anything in PERL for at least 10 years, and I never was really highly skilled at it to begin with. So I've had to go and relearn it from scratch pretty much, and an experienced PERL programmer will probably look at this code and say, that's horrible code, but it doesn't matter because it works. And that's all I care about. So, as with most assemblers, it's 2 passes. The first pass just builds the symbol table, and the second pass actually generates the output files. Since the generated microcode is 24 bits wide, it generates 3 hex files for the high byte, the mid byte, and the low byte, which can then be loaded into the programmer. Those are in Intel hex format, and they're encoded in the least efficient manner you can as a single record per byte. But again, I don't care. Maximum amount of microcode you could have is 4K words, and reading in 4096 records, no big deal. It also generates a listing file. The listing file shows the line number, the address, the code generated, and the original source code line. It's like 9 pages of PERL, so. Okay, the reason for using PERL was I can knock something out quickly, it's highly portable, and like that. So I've called the assembler MCASM for Microcode Assembler.pl. To run it, you do PERL MCASM.pl, and then the assembly code name, which in this case, I've written a test program, which is called mctest.mic. The MIC is for microcode. You add your KEY and your MOUSE, and what do you get? I don't know. So the command line PERL mcasm.pl mctest.mic. Boom. Pass 1 takes all of 2 milliseconds. It shows the number of symbols and the number of statements in the program. Pass 2 takes 45 milliseconds. And then we have our output files, mctest.lst.high.mid and .low. .mid, Windows thinks is a MIDI file. Brilliant. So I should probably change those so they're .hex extensions. Should probably be mctest-high-mid-low.hex. I'll get around to that at some point. So now, to load those into the flash memory, we bring up the programmer, open the file, specify Intel hex format. Boom, that loads it in to memory, and then we can press burn and write it into flash. And that's all there is to that. Now, the test program. I decided I want to make use of the front panel switches to make sure that's all reading correctly. And I want to make use of the lights, of course, to make sure that, so we can visually verify that the registers are getting set correctly. So what this will do, when you reset, it's going to set all the registers to 0. And then we have 9 switches. Okay, so here's what the switches are going to do. Examine loads the front panel switch value into the memory address register. So you press examine, whatever's there goes there. Examine next increments the memory address register. Deposit moves the memory address register to the accumulator. Deposit next swaps the accumulator and the program counter. Those top 2 sets of lights there. Start rotates the accumulator left through the carry. So we can march a bit down and through the carry and wrap it around and bring it back around, and then continue rotates it right through the carry. So we can go back the other way. Step outputs the contents of the front panel switches to the TTY, which we kind of saw in a previous video where I had it hardwired, but now it's doing it through the microcode. Load will actually put it into a mode where it echoes the TTY, the terminal in, to the terminal out until it sees a null character. So until we press break. So I can press load, type away, and when I press break, then you'll see it no longer echoes. So it's gone back to reading the switches. And finally, stop will jump to microcode location FF3, which will display 0011 on the error lights. And you have to reset to get it out of that state. So that's the current state of things. What we've tested is that the front panel switches and the front panel lights are working properly, that we can move things between registers, that we can branch conditionally and unconditionally, that we can do terminal input and output, and that we can do operations on the registers, like arithmetic operations, and that we can display an error condition, of course. So the next thing to do is install the memory and make sure that works, and/or get it working, and proceed from there to generate the actual microcode for the stupid computer itself.